Okay, so in this problem we have a simple little mechanism. We're told that link AB is extending at a rate L dot. Omega 1 is a constant rate of rotation, omega 2 is a constant rate of rotation, and at the instant shown, the link AC is aligned with the fixed capital Y axis. Based on this information, we're asked to determine the velocity of end A, the telescoping rod, and also find the acceleration at the same point. So in this regard, I'm going to start by finding the angular velocity of the rotating frame. I'm going to note here that the capital X axis is actually pointing out at us into the screen, and so this means this is going to be omega 1 about the capital Y axis, plus in this case, a rotation about the capital, in this case I should say lowercase z axis, and let me see here by right hand rule whether that's positive or negative. It looks to me that's going to be negative, so we're going to have minus the rate omega 2 about the little k axis. Now I can write that in a consistent vector set later on, but for now let's go ahead and compute the angular acceleration of the rotating frame. So by the product rule of differentiation, I know this is going to be equal to omega 1 dot in the capital I, plus omega 1 in the capital I dot, minus omega 2 dot in the lowercase k, minus omega 2 in the lowercase k dot. If I note that my rates of rotation are constants, the first and third term will go away. And if I note that the capital Y axis is a fixed axis of rotation, the second term will go away as well. This is going to leave me with an angular acceleration equal to minus omega 2 times quantity omega across lowercase k. If I do some substitution here, I can re-express this as minus omega 2 times quantity omega 1 in the capital I, minus omega 2 in the lowercase k, and I'll cross that with the lowercase k. At this juncture, I'm going to ask you to note that the upper and lowercase axis sets are coincident at this instant, so I can replace the capital I by lowercase i's in both the angular acceleration and angular velocity formulation. This will leave me with an angular velocity given by omega 1 in the little I, minus omega 2 in the little k, and an angular acceleration given by, well, noting that k cross k goes away, I'll have omega 1 times omega 2 in the lowercase j direction. Now that I have that, I can start to find the velocity and acceleration. So I'm going to start by finding the velocity of point A. So I'm going to note the velocity of point A is going to be given in this instance by the velocity of point C plus the velocity of A with respect to C as seen by our observer. The observer, of course, will be standing here at C, the origin of the rotating frame, plus the angular velocity of the observer across R of A with respect to C. Now to do this properly, I'm going to start by finding the velocity of point C. We'll note that the velocity of point C is equal to the velocity of point O, plus the angular velocity of link OC crossed with R of C with respect to O. This is going to equal 0 plus omega OC, which is the rate omega 1 in the capital I, crossed with R of C with respect to O, which is a distance d in the little k direction. Again, I'll note here that the capital and lowercase i's are coincident at this instant, and that's going to allow me to work out here to get a velocity given by minus omega 1 times d in the lowercase j direction. I can then take that and find the velocity of point A, so it's going to be the velocity of point C, which we just found to be minus omega 1d in the little j, plus the velocity of C with respect to A relative to the observer. They're going to see just the extension L dot in the little j direction. I'll add to that the omega of the rotating frame, which is omega 1 in the little I, minus omega 2 in the little k, and I'll cross that with R of C with respect to, R of A with respect to C, which is a distance L in the little j. If I work this out, I'm going to have minus omega 1 times d in the little j, plus L dot in the little j. I cross j is k, so I'm going to have plus omega 1 times L in the little k. K cross j is minus I, so I'll have plus omega 2 times L in the little I. From here you can plug in numbers and find a final result for the velocity of point A. I can then proceed to find the acceleration of point A, and the way I'm going to do that's going to largely mimic what I did with velocity. So I'll say the acceleration of point A is equal to the acceleration of point C, plus the acceleration of A with respect to C, as seen by the observer, plus the angular acceleration of the rotating frame across R of A with respect to C, plus the Coriolis term, which is 2 omega across the velocity of A with respect to C as seen by the observer, plus the triple product term, which is omega cross quantity omega across R of A with respect to C. If I go ahead and make some substitutions here, I can get the final result. So to kick us off in that regard, I'm going to start by noting that the acceleration of point C is equal to the acceleration of point O, plus the angular acceleration of link CO across R of C with respect to O, plus the omega of CO, cross with quantity omega of CO, cross R of C with respect to O. If I note that the rotation rate for omega CO, that is omega 1, is constant, the second term here will go away. And if I note that O is a pin joint, the first term is going to go away as well. This is going to leave me with an expression for AC given by, in this case, omega 1 in the capital I, cross with quantity omega 1 in the capital I, cross with R of C with respect to O, which is a distance d in the little k. If I note that the little I and big I's are coincident at this instant in time, you can work this out and find that's equal to minus omega 1 squared times d in the little k direction. Now that I have that, I can go ahead and substitute things back in to find the acceleration of point A. In this regard, I'm going to find that the acceleration of point A is equal to the acceleration of point C, which I just found to be minus omega 1 squared times d in the little k. I'll add to that the acceleration of A with respect to C relative to the observer, which because L dot's a constant will be 0. I'll add that to the angular acceleration I've found up above, and let me go back and get that for you. It's omega 1, omega 2 in the little j. I'm going to cross that with R of A with respect to C, which is a distance of L in the little j. I'll add that to the Coriolis term, which is 2 times omega. Let's go up and get omega. Omega is omega 1 in the little I minus omega 2 in the little k. And I'm going to cross that with the velocity of A with respect to C relative, which is L dot in the little j. I can then add to that the triple product term, which is omega 1 in the little I minus omega 2 in the little k, cross with the product of omega 1 in the little I minus omega 2 in the little k, cross with R of A with respect to C, which is L in the little j. If I work out my cross products here, I'm going to have that the acceleration of A is equal to minus omega 1 squared d in the little k. J cross j goes away, so I'll get nothing from that third term. I cross j is k, so I'll have plus 2 omega 1 times L dot in the little k. K cross j is minus I, so I'll have plus 2 omega 2 times L dot in the little I. And then from the triple product term, I'll have plus quantity omega 1 in the little I minus omega 2 in the little k, cross with the result of this cross product here. I cross j is going to give me k, so I'm going to have omega 1 times L in the k, and k cross j gives me minus I, so I'll have plus omega 2 times L in the little I. As a final step here, I can work out my last cross product, and I'll get the acceleration of A is equal to minus omega 1 squared times d in the little k, plus 2 times omega 1 times L dot in the little k, plus 2 times omega 2 times L dot in the little I cross k is minus j, so I'll have minus omega 1 squared times L in the little j. I cross I goes to 0, k cross k goes to 0, k cross I goes to j, so I'll have minus omega 2 squared times L in the little j. From here, all you need to do is plug in numbers. It was a long path, but we made it. Best of luck, everybody. Take care.